Okay, so we'll begin today with the next chapter, chapter 2, that deals with functions. And the first section, basics of functions and their graphs. And the summary, as the authors often do, and the objectives that are to be learned, which don't really mean a whole lot at the very beginning, but then you can see as we go along how they are relevant. So, first of all, even though this is very, very basic in math, you often have a need to have two numbers written together. And so that's just called a relation. And normally when you think of graphs, you have an x and a y value. And so the first of those values, the x values, is the domain, and the second value is called a range. Now, you can list them by graphing them. You can list them by writing them down in various ways. So if you have a bunch of ordered pairs, such as you see right here, that's a mathematical relation, but you simply know that the first value, or the x's, consist of the domain. The second value consists of all of the values of the range. And these little curly braces around the ends are the ones that are commonly used to designate a set of values. Now, what's most important is a function. Now, it's used so often that it's easy to forget that there's a formal definition behind it, but here's what it is. A function is a correspondence from a set called the domain to the range such that each element in the domain corresponds to exactly one element in the range. Now, as before, that's abstract, so here's examples. So this is a mathematical relationship. But is it a function? No, it's not, because there's two different values of the domain, the 6, that each correspond with a different value of the range. So otherwise, if you have all different values of the domain and all different values of the range, then it is a function. But this one particular case makes it not a function. Now, what's a little bit confusing, and is why I put this example right here, is notice that each element of the domain is different, the 5, 8, 6, and 9. So if there's always a different element in the domain, then it will be a function. But it is possible to have different elements in the domain, the 5 and 9, correspond with the same value of the range, and that's what makes it a little confusing. So this is a function, and the formal definition is not something that you need to really worry about too much, because there's often graphs that are done, and the graphs, as I'll show you in just a little bit, make it a very easy way to indicate whether something is or is not a function. All right, so when we write functions as equations, then we have y in terms of x. So these are examples right here, but notice this particular one where you have an x squared and y squared. When you want to make y the subject of the equation, or y on the left-hand side, and since it's a square, since you have y is equal to plus or minus the square root of this entire quantity, then because of that, it would show that that is an example of a relation that is not a function, because y could correspond to positive value, and the same value of y can correspond to a negative value. So that's an example of not a function. All right, normally you have values written as equations, y equals something. But another way to emphasize the functional notation is to put an F and then have parentheses. And when you see that, you say in your mind f of x, that's most common, or f at x. All right, so this really is not that hard. There's so much vocabulary to go with it that it looks like it's really hard, but I don't think it is. So if you have this function, f of x equals all of this right here, to evaluate means you have a specific value of the function with each value of the domain, and remember domain is x. So f of 5 simply means that everywhere you see an x, -5, you put in a -5 and then just work it all out. So that's all there is. So it's -5 squared minus 2 times -5 plus 7, and you work it out. So f of -5 would equal 42. So another example then, f of -4, once again, only means you substitute in -4 in each place of the x and work out the value. So 3 times -4 squared minus 6 times -4, and as I believe I mentioned last week, be so careful about these negative signs as well as this one right here. And when you enter the number in the calculator, when you do -4 squared, make sure that the -4 is inside the parentheses, because that's the only way of the syntax of your calculator to recognize that. All right. Now, a graph, of course, is something that is used over and over because a picture representing points is a good visual way to illustrate what's going on. So here's an example. If f of x equals 2x and g of x equals 2x minus 3, one way to graph them is simply to plot a bunch of points. So if you have this first function, f of x equals 2x, you can just put down various values of x and then work out various values of f of x. But remembering that f of x is synonymous with the y coordinate, and then you just plot the points. So when x is -2, then y is -4, x is -1, y is 2, x is 0, y is 0, and so on, and then you draw the straight line. So that's the graph of f of x. G of x is this function right here, and once again, plotting points in there, then you just connect all of the points and you have the graph of the function. All right, now I mentioned a moment ago about how there's a very short, simple way that you can quickly and instantly look at a graph and see whether or not it is a function. Remembering, as I said, that every value of the domain has a unique one and one only corresponding element with the range. So what does that look like when you have a graph? Well, it looks like this. So the vertical line test means on every vertical line you have the same x value, which is the domain, but you have a different y value, which is called the range. And that's the requirement that you can't have to be a function. So very simply, just think of a vertical line, and if you can put a vertical line at any place through the function and it intersects at 2 or maybe more points, then that is not a function. That makes it very easy to work with. Now notice, if you could imagine this blue vertical line, if you moved it from left to right, everywhere on that function, then you would intersect the graph at only one point. So this is the graph of a function. So just remember the vertical line test, and you can easily determine whether it is or is not a function. Now, notice, even though this graph looks very, very strange here because it's a complicated function, which we're not going to get into, other than to know how to read graphs. So first of all, it says use the graph to find f of 5. So remember, f of 5 means what is the functional value when x is 5. So you go, of course, to the horizontal axis for x. When you get to 5, you go up to the corresponding point on the graph, then you go across, and it is 400. So f of 5 is equal to 400. But of course, we're all aware that so many of the functions and principles of math you have to think of in both ways. So nextly, what is the value of x if f of x equals 100? So if f of x equals 100, that means that's the y value. So you would go all the way down here to 100, which is the y value of the graph. You go straight across until you get to this point where it intersects the graph, and the x corresponding value is 9. So that means f of 9 is 100, so the value of x is equal to 9. Now, since this idea of domain and range really are important as requiring you to know about possible values for the function, let's think about looking at a graph and thinking about the domain and the range. So here's again a strange looking graph, but it's a mathematical function, because remember the vertical line test, it intersects the graph at one place only everywhere you draw a vertical line. But if it went from this endpoint to this endpoint here, notice that the x values go left to right from -2 to 1. The y values go vertically from 0 up to 3. So you can write this expression as saying the domain is the set of all x such that -2 is less than or equal to x and x is less than or equal to 1. Or you can use the square brackets to indicate that the endpoints -2 and 1 are included. The range, being the vertical values, goes from 0 to 3, so y is a set of all values such that 0 is less than or equal to y is less than or equal to 3. Okay. Now notice in this case the only one that's different is this open circle right here means that a graph goes right up to that point but does not include it. So that's why you have this open or curved parentheses here to show that -2 is not a part of the domain and to show that +2 is not a part of the range. All right, now let's think about this right here. So I put this extra slide in here because to try and hopefully make it a little more clear. So remember, the blue line is indicating only whether there is a one-to-one correspondence, which again is why this is not a function, but the one on the right is. So let's think, what is the domain and range of each of these functions? So when you look at the graph, notice that this graph keeps on going forever, which is the point of these two arrows at the end. But notice that the values of x do not extend to the left. All right, now keep that in mind when now we look at the second function on the right. Notice that these y values keep on going infinitely higher, but the y value itself does not extend down any lower. So to think of the domain and range means, for the first one, the domain is a set of all x such that x is greater than or equal to 0. So x does not come to the left, it only starts here and goes to the right. However, the y values, even though it's not really plain, it does keep increasing gradually, and so it will get higher and higher, and this one will get lower and lower. So this symbol means -infinity to +infinity are the y values. And then for this one over here at the right, notice that the x values can keep getting infinitely smaller or infinitely larger. So that's why this is the domain. But the values of the range can only go from 0 and higher. So this is a value of the range. Okay, any questions up to this point about these ideas? All right, one very important way of thinking about graphs is what's called the x-intercepts and the y-intercepts. And as it says, a function can have more than one x-intercept, but at most one y-intercept. So what this is showing right here, you see the 3 red dots indicate the x-intercepts. Now intuitively, this is where oftentimes, or sometimes anyway, there's confusion. The x-intercepts are where the y value of the function is 0. So if you think about each of those 3 red dots, the y coordinate is 0, -3, 0, -1, 0, and 2, 0. But then conversely, the y-intercept in the blue dot is where it crosses the y-axis at -6, but the value of the x-coordinate is 0. All right, so once again, we're okay so far up to this point. All right, next section is to go even more in detail about the graphs. So we'll look about various intervals as well as the concepts that are called relative maxima or minima. And those words maxima and minima are plural, meaning the maximum point or points, minimum point or points. And piecewise means you divide the function into 2 or more places. All right, so as before, even though you see a very formal looking definition which is required in mathematics, I hope that you can just look at the graphs and be able to intuitively understand what's going on. So even though that previous slide was so complex in the definitions, here's what it means, and it's very obvious, intuitive. This function that you see the graph here is increasing from -infinity to -1. So when you think about increasing and decreasing, look at your function as you would normally read it, going from left to right. So everywhere from -infinity for the x values all the way until you get to the x-coordinate of -1, the function is increasing. Then from -1 to +1, the x-coordinates show the function is decreasing, and then after +1, the function keeps on going forever and is increasing. So that's the idea of increasing and decreasing. Similarly, this is a very complex looking definition for relative maximum and relative minimum, which is why the graphs really are very valuable ways of understanding mathematical relationships. Just listing a whole bunch of points, you're going to get so complicated without seeing what's going on, but a graph aids that. So what is a relative maximum or relative minimum? Now think about the term relative in contrast to absolute, which of course has a very similar correspondence within a Christian worldview, where you think about relative truth versus absolute truth, which is what the scriptures teach about. So notice that since this function keeps on going forever in a negative direction and forever in a positive direction, there is no absolute maximum, there is no absolute minimum. So relative means just around these points right here, when x is -1, that's a relative maximum. And then just around these points a little bit to the left and to the right, that's a relative minimum. So I think also that intuitively you can look at that and see what's going on. Okay, A piecewise function means it's defined by two or more equations over a specified domain. So here's an example where you have c of t. Now, even though they're using t instead of x, it means the same thing. So you could have c of t or c of x is equal to this constant only for all values of the domain between 0 and 60. But then it equals another value if t is greater than 60. So you could also show the functional values. This is piecewise. You have one value of the function for all the first values of the domain. Then you have another expression for all of the second values of the domain. And so remember, as I previously said, you can always plot points to get an idea of what the function looks like. Although, as we'll see very soon, these ones are straight lines, which of course are the most simple ones to work with. So what does that look like? Here's the definition. Piecemeal means two parts. So f of x is equal to 3 if x is less than or equal to -1. So no matter what the value of x is, the y value is always 3. So that, of course, is showing that's a straight line. But then going back from the points that were plotted right here, for the rest of the function, you can see it's going to be this line going right here. So that's what a piecemeal function is going to look like. All right, so we're all staying with this okay. All right, but once more, we do have to do more with graphs. So in particular, linear functions and slope. So linear, of course, is the adjective form that comes from the word line. And so we'll be working with lines. They are the most commonly used types of functions, the most commonly recognized graphs, and thankfully the easiest ones to work with. But there are different characteristics. First of all is slope. So what is slope? Well, a formal definition is a change in y divided by change in x. Or the simple words that people often use is rise over run. Now notice that you have to think what those words mean. So rise, of course, refers to a vertical change, and run refers to a horizontal change. So notice that this word slope must be referring to a ratio. It's a comparison of two numbers. So that's different from thinking about a constant. You can talk about some constant. How many chairs are in this room? That's a constant, one number. But a slope is always a ratio. And since the y coordinates are vertical, you find the difference of two y values, and then you divide by the difference of two x values. But notice there's this restriction. The denominator cannot be equal to 0 because division by 0 is impossible. And so we'll work with several examples right here, but that's a very important definition to remember and will be needed in homework problems. So, how do you find the slope of a line that goes through 2 points? So if we had a graph, you could easily plot these 2 points, 4 to the right, -2 to the bottom. For -1,5, you'd go 1 to the left and then 5 up, so you could have those 2 points. What is the slope of the line that passes between those 2 points? So it's a difference, since it's a change. Second y value, subtract the first y value. Second x value, subtract the first y value, x value. And so you get 7 over -5, which is the same as just saying the fractional change is -7/5. So that's one that is frequently used. Now, since the lines are so commonly used, there are 2 common expressions for those lines. One, that is an equation. One is called the point slope form. So it means just what it says. It means you have a specific point, and this letter M is commonly used to represent slope. So this is the general form. Now notice carefully that y1 and x1 refer to specific points, whereas x and y can be any values at all. So in doing algebra, which you are all aware of before, it requires doing neat work. So here's the task ahead. Write an equation in point slope form of the equation that has a slope of 6 and passes through this point. Now notice before we go on, because I mentioned a moment ago that slope is always a ratio, but they've just got one number right there. But if you think about it, that's not a problem, because every whole number can be written as a fraction of that whole number over 1. So technically this is a ratio of 6 over 1, but since it's over 1, it's not necessary to put it there. So this is the form right here, and you just substitute in values. Y is -5, x is +2, and the slope is 6. So then of course you simplify onto the right-hand side, and so this form right here is called the point slope form of the equation. So the reason why that's useful is if you wanted to know what does this line look like, you need to have only two facts: a point that it goes through and the slope, and you could immediately tell what the graph looks like and neatly and easily graph it. And then the same thing with what you have right here. Now, even though that is the point slope form, I went ahead and expanded this out and multiplied, distributed 6 times x minus 2, took the 5 over to the other side, because in just a few moments we'll notice that this is a different form of the equation that has a different name, but also is relevant to working with lines. All right, so let's see if you can take your sheet of scratch paper there handy and see if you can show me how would you write an equation in point slope form that has the slope of the fraction 2/3, and it passes through this point right here. What would be the equation in point slope form? So you can put this as x plus 6. X minus -6 is the same as x plus 6. And this is fine right here. Now, this is all that's needed for the point slope form. But notice carefully here, this one, when you distribute, and you've got the plus sign here, which is good, but, oh, okay, that's good, that looks fine. Almost there.
Yeah.
Now again, this is all you have to do for the point slope form, which is fine right there.
Oh, I thought it solved for y. Okay.
And that's perfectly fine, and that is what I did also. But again, it's not to be confusing to all of you, but to notice that the point slope form is just this right here. You don't have to extend it out any further.
Okay.
However, when you solve for y and you get it in this form, that's relevant to actually this very next concept. So you have it all correct. But the next one is called the slope intercept form. So the previous one was point slope. This one is slope intercept. And now you have a different looking equation. Yes, y equals mx plus b, where m still refers to the slope, but now this new constant b is called the y-intercept. So that's what was actually the second form from the previous problem, would tell you that the slope is 2/3. Obviously that hasn't changed, but a y-intercept means just that. It's where the graph crosses the y-axis. So all you have to do is just what it says right here in these 3 points. So if you had a different equation, y equals 3/5 x plus 1, that's in the slope intercept form. So the slope is 3/5, the y-intercept is 1. So if the y-intercept is 1, that means it's the point where the function crosses the y-axis. So you put a dot right there at that point. But then since the slope is 3/5, remembering that the numerator refers to the vertical change, the denominator refers to the horizontal change. So to graph the line, you start at the y-intercept, which is 1 right here. The slope is 3/5, means the rise, vertical change is 3, the run is horizontal 5 units to the right. So you go up 3 units, 5 units to the right, you get to this point right here, and then you simply draw a straight line that goes through those 2 points. So you can easily see how knowing those 2 facts also allows you to immediately plot the graph of the straight line. All right, so questions about those 2 forms? All right, then we need to look at 2 special cases, and one of them is the horizontal line. So notice a horizontal line only is in this form right here, where b is the y-intercept. So the slope of a horizontal line is 0, which means even though this is the best, simplest form of the equation, you could technically put down y equals 0x plus b, but of course since 0 times x is 0, that part is not necessary. So as an example, if you were told to graph the line y equals 3, all you would know is that the y coordinate is 3, and it doesn't matter what the x coordinate is right here. That's why you only have y values. So again, this is a little intuitively different because you think, well, y, doesn't that refer to the y-axis going up and down? And it does, but since the equation says y equals 3, that's telling you that the y coordinate, as I just said, is 3 no matter what the x value is right there. Now, I'm sure you can imagine that the next thing to look at would be a vertical line. So if you have x equals a, then that's the equation of a vertical line. But be real careful to note that the slope of a vertical line is undefined because you would have a change in y coordinates but no change in x coordinates, and so the denominator of the slope would be 0, which again is undefined. So if you needed to graph a vertical line that goes through this point 7, 0, then the equation of that would simply be x is equal to 7. So notice real carefully here, as I was just hinting at. If you had a different example here, if a vertical line passes through 3, negative 5, and then it also passes through 3, 7. So notice why that's not a function, by the way. You have the same x coordinate but different y coordinates. And so if you are actually trying to calculate the slope, then by doing the form, you would have the change in the y values divided by the change in the x values, which is 12 divided by 0, which is undefined. Now be also clear in your minds, because I know from previous experience people can get this confused. The slope of a vertical line is not 0. To say the slope is equal to 0 is different from saying that the slope is undefined. It just doesn't exist. That's why you say that phrase, doesn't exist, means it's just not possible to have. All right. So even though those are the two most common forms, the point slope form and the slope intercept form, there is a third way of expressing the equation of a line, which doesn't really tell you what it looks like, but it can aid you in graphing the line. So if you have A, B, and C are real numbers, but A and B are both not 0, you can write the line in this form right here, which is a valid way of expressing it, but the disadvantage is it doesn't really tell you what the line looks like. But you can easily figure that out, because if you take this original equation of the line right here, we can always change it to the slope-intercept form by setting the equation equal to y. So you take the 3x and the negative 12 to the opposite side, and then of course you would divide everything by 6. So now you have transformed the original equation into a different form, and now you know what the slope is, now you know what the y-intercept is, so you could easily graph it from there. So that's one thing that can be done. However, another option, and notice these are different ways of doing the same problem. You can find the two intercepts, the x-intercept and the y-intercept. So what you would do for an x-intercept, you would just let y equal 0, solve for x. For the y-intercept, let x equal 0, solve for y, and then take a ruler or a straight edge, drawing through those 2 points. So what does that look like in particular? All right, so here's the graph, the equation we were just working with. To find the x-intercept, you assume that y is equal to 0. So you substitute 0 in place of y, you get this simple equation, x is 2. So an x-intercept means x is 2 and y is 0. So we've got the first point. Then we do the next. For finding the y-intercept, let x be equal to 0, substitute 0 in place of that, work it all out for your equation. So you notice, of course, there are always going to be several steps to the equation, but they're not hard. So y is negative 3. So x is 0, y is negative 3 is the other intercept. So then you just take those 2 points. 2, 0 we got first was the x-intercept. Negative 3, 0 was the y-intercept. And then, of course, just by connecting a straight line and showing that it does go on forever. Now, of course, it's very easy to forget to put the 2 little arrowheads on the end, and that's not a problem in doing your graphs, but just remember that the domain and range of the straight line are negative infinity to positive infinity in both cases. All right, one more quick example from this section would be to note that you can have an application problem. In this case, it's talking about temperature, and you can get big, long, complicated looking decimals for x and y, but still you can work it out in exactly the same way to find slope by finding the difference in the y values divided by the difference in the x values. And of course, you know, in those particular cases, the graphs are representing close but not perfect values. So this little symbol right here means equals approximately, and that would be the approximate slope. All right, so 3 basic forms of the equation. So no questions about those then. All right, then we'll continue on. There's another idea that's actually a couple of ideas that are relative to the types of lines that are commonly worked with. And those are parallel and perpendicular. All right, so you know what parallel means. That's easy to understand, and we'll get to that in just a minute, and also perpendicular. So as before, they're describing what has happened here, and the first point is to note if you have lines that are not vertical and they're parallel, they have the exact same slope. But any 2 vertical lines are parallel, and any 2 horizontal lines are also parallel. So now's where we get moving up to a little more difficulty in thinking about how can you solve what's going on. So be sure that you clearly read and understand the question. Here it is. Write an equation of the line passing through this point that is parallel to the line that you have this equation. So you can think for y equals 3x plus 1, you could easily graph that line. Somewhere else, there's another point right here, and you want to have a line that goes through this point but is parallel to this line right here. All right, so how do we go about doing that? All right, first of all, for the first line right here, you immediately know it's in slope-intercept form, so the slope is 3. Next, since the line has to go through this point, we use the point-slope form. So x is 5, y is 5, x is -2, but the slope is 3. So you use the point-slope form, change it into this, then distribute the 3, add the 5 to the other side, and so here's the new equation. So think about what you have accomplished here. You have now written a different equation for, of course, a different line, but it goes through the point -2, 5, and it has the same slope as the original line, so they've got to be parallel. And as a check, even though you don't have to, does this graph y equals 3x plus 11 go through this point -2, 5? Well, to do so, substitute in -2 in place of x. 3 times -2 is -6. -6 plus 11 is 5. Y is equal to 5, and that's what that point is supposed to be, so you've got it. All right, so let's look at another example right here. So, if you want the line to go through a different point parallel to the first, remember it's a 2-part problem. Write the first equation in the point slope form and then in the slope intercept form. So, once again, if the original equation has a slope of -3, that's what you work with. But if it's going through 8, 5, then you have point slope form, y minus 5 equals -3 times x minus 8, which is the slope intercept form, the point slope form. and then you convert that into the slope-intercept form. So this line right here and this line right here would be parallel. And do you notice something else that's interesting about these? You can see that on the first line at the top, the y-intercept is positive 6, but on the second line down here, the y-intercept is 29. But since the slopes are negative, then they are going to be parallel, but just passing through different y-intercepts. All right, the next thing we need to look at is the ideas of parallel and perpendicular, or well, we did parallel lines, but now what about the slope of two perpendicular lines? So of course, perpendicular means it's where two lines intersect, but they form right angles or 90-degree angles. That's what it would look like on a graph, but to look at the equation of it, if two non-vertical lines are perpendicular, then the product of their slopes is -1. So remember, product means one number times another number. So another way of looking at that is if their products equal -1, then the slopes are negative reciprocals of each other. So perhaps you can recall to mind a reciprocal is where a numerator and denominator of a fraction are turned and reversed. So 3/4 is a reciprocal of 4/3, but positive 3/4 and negative 4/3 are negative reciprocals, or some people refer to them as opposite reciprocals, which means the same thing. But notice that the first one times the second one, in this case, would be -12 over +12, which of course does equal -1. Then you have the special case about horizontal and vertical lines. They are always going to be perpendicular to each other. So how do we go about making a new equation that is perpendicular to a given line? All right, so here's what we have to note. Just think through every single aspect of the problem. They involve slope. So if you have an equation that looks like this at the beginning, we don't know what the slope is until we change it into the appropriate form. So take the x to the right-hand side, take the -12 to the right-hand side, gives you this. Divide by 3 on all of the terms, and so then immediately you can tell that this slope of this line is -1/3. So the negative reciprocal would be making it into 3/1, and it would be positive. So the slope of the perpendicular line would be positive 3/1. Then this brief introduction to this idea that slope really is a rate of change. That's exactly what the idea means. It's a change in the y values divided by a change in the x values. So it describes how fast a y coordinate is changing with respect to x, or as they're talking about these other values of dependent and independent. So the independent variable is x and the dependent variable is y, but the concept is simply that it is a rate of change. And so actually you can see rate of changes sometimes expressed as percents. I've seen road signs where it will say there's a 2% grade or a 3% grade. Well, that means it's a rise of 3 compared with a horizontal run of 100. So a percent is a way of expressing a rate of change. So here's an example of what they were talking about. The change between two different years from 1990 to 2008, when approximately 9 million adult men lived alone, and then compared to the next year of 14.7. So you have an X value and a Y value, an X value and a Y value. So what is this going to be as a rate of change? Well, the concept would be exactly the same. That is, you have these two various X and Y coordinates. So M, representing the slope, would be the Y values divided by the X values, and then you work it all out and you get this value, which is the slope, or the slope, of course, is the same thing that's going to be expressing a rate of change. All right, so again, anybody with questions about parallel, perpendicular lines, or slopes? All right, so this leads us to the next section, which will be, I believe, a very good time for us to take about a 10-minute break, and then we'll start again. So we're still looking at graphs and their functions, but now we look at this concept called transformations, which simply a transformation in a graph is simply a movement. And this is primarily involved with special relationships where you have either vertical or horizontal shifts or changes in functions. So the next several slides, I want to show you basic forms of very common functions, but don't at all get intimidated or bogged down in these details. These are not questions whereby I'm going to emphasize this as far as knowledge that you need to know for a test, but to help you get a better idea of what the basic forms of the equations are. So there's a constant function, a linear function, absolute value, a quadratic or a square, square root, a cubic, and a cube root. So a constant function is just a horizontal line, never changes. So the domain and the range are infinity. A straight line, we've also looked at that, same idea. The absolute value function, if you recall, the absolute value is a mathematical formula whereby a negative number becomes a positive number stays itself, and so the absolute value function will look like this, where there's a restriction on the range since the range only is positive. A quadratic, which will be part of what we'll look at in later chapter, is a curve that looks like this, that has infinite values for the range, but only going from 0 to infinity. The square root function, you can see, only goes like this, and the reason there's no values to the left is because a square root of a negative number is not defined, so you don't have a graph representing that. A cubic function looks like this, and a cube root function looks like this, noticing that you can have cube roots of negative numbers. For example, the cube root of -8 is -2 because -2 times -2 times -2 is -8. So what does it mean to have vertical shifts? So for example, here printed in blue is the basic form of the function absolute value of x. But if you have absolute value of x plus 3, then of course you can simply see that a vertical shift just means it goes up or it could go down, but the shape of the function doesn't change. Now, if you have f of x plus c or f of x minus c, then the graph can shift either to the right or to the left. So if you have f of x equals square root of 4, which looks like this, if g of x is the square root of x minus 4, it shifts to the right, which is not intuitive, but if the value is a minus, then it shifts to the right. If the value is plus, it shifts back to the left. So that's all I'm going to say about the horizontal and vertical shifts of the graphs. But it is, I believe, more relevant and needed to think about what's called combinations and compositions of functions. So here are the objectives we'll look at over the course of the next several minutes. All right. And they're talking here about all possible values of the domain. So in most cases, the only thing to look at is where is the function possibly not defined. So if they're straight lines, for example, you never have to worry about this because the function is always defined. So in reality, this is one of those situations where you want to analyze characteristics but from a negative perspective. What cannot take place? So here's a good example. If you have, and by the way, these phenomena occur so often when you have division and when you have square roots, because those are the two common situations where you can have undefined values. If you have this function, this mathematical relationship right here, you want to find out what possible values could make the denominator undefined. We don't care about the numerator, that's always defined. But in the denominator, if x squared minus 49 equals 0, and you work that all the way out, you would get plus or minus 7, which tells you that you can have any number for the domain except 7 or negative 7. So if you wanted to write it out in the words, you could say the domain is all real numbers except negative 7 and positive 7. The formal way the authors write this is it's everything from negative 7 to 7, from negative 7 to positive 7, and then from 7 to positive infinity. That's just a formal mathematical way of writing it out. All right, you can take any set of functions and combine them together by adding and of course subtracting or multiplying or dividing. But as I just said, the special cases to consider for restrictions on the domain are division. But for addition, subtraction, and multiplication, you can do anything with them and there's no restrictions. Now, let's keep in mind real carefully this word combination. In contrast, in a couple minutes, we'll work with composition. And it's unfortunate that this is a case where you have two words that look similar but mean something different. So combining just means you take two different functions, you add, subtract, multiply, or divide them. So if you had this function, f of x, x minus 5, g of x equals x squared minus 1, if you combine them by adding them, then there's no restriction in the domain here, and so there's going to be no restriction here. So when you combine the two functions, you just do what it says. You add, subtract, multiply, or divide, so the domain is still going to be all values from negative infinity to positive infinity. So I'll not have any more slides about that because that's all you do. A combination means you take a given function and then whether you're told to add, subtract, multiply, or divide to the second one, and you get a new function. Composition is something that actually occurs quite a lot, but it's not recognized. It's really a function within another function is what it really means. And I'll have you work a problem here in just a minute to make sure you can understand it. So the composition of a function f with g is denoted by f and then this little circle right here. F composition of g. Now, you can write it in this symbolism, but it also means f of g of x. So that's why it's a function of another function. It's not combining them as if you were adding, subtracting, multiplying, or dividing. All right, so let's look at specific examples. Here's what's going on. So suppose you had this original function, f of x equals 5x plus 6. G of x is 2x squared minus x minus 1. So what is the composition of f and g? So this symbolism here is good. I personally prefer this symbolism to help you understand really what's going on. What it means mathematically is f of g of x means you substitute the g function in place of every value of x in the f function. So if you can keep that in mind, substituting every value of the g function in place of x. So the g function is this. So if you put that function in place of the one x value here, so it becomes 5 times this, and then you have a plus 6. So that's all you have to think about really, is substituting the inside function in place of the outside function. I know that's not really good math terminology, but that's really what it means. Then, once you get it in this form, distribute the 5 all the way through, simplify it out, and you have a composition of functions. Okay, now hopefully that's clear what I just said. To reiterate, if you have f of g of x, you substitute the entire g of x function in place of this right here. But if I had said g of f of x, it would be just the opposite. G of f of x means you would have had to take this whole expression right here and put it in place of this x and in place of that x right there. All right, so let's see if you can all work out a couple of examples right here. Now, I made these shorter so you don't get lost in the details. So take a sheet of scratch paper and see if you can evaluate and simplify. First of all, f of g of x, and then secondly, g of f of x.
Do you want them solved or just?
And I'll show you that on the next slide, but we'll see if you're on the right track. So, oh, I didn't do that wrong. Okay, so yes, you do have the right answer on the first one, and the second one is correct at the beginning. And then what you need to do is to go ahead and expand this one out. So you have solved that first. Now expand this out and then simplify.
We could factor this out. Is that what you mean?
Factor what I just said. This one you need to simplify out more too. So expand and distribute the 3 through here. 3 times x squared and 3 times 15, and then minus 8. So this one you would expand out by taking 3x minus 8 times 3x minus 8 and expanding it out.
Okay.
So you're on the right track for sure. And so that one is correct. Yes, it is. Now, no, that one is not correct because this function, let's see, so you have to put g composition f means g of f of x. So then this right here goes in place of this x right here. So it's going to be 3x minus 8 squared. We forgot the square, yes. And then, of course, the plus 5 also at the end. So go ahead and take that. 3x minus 8 times 3x minus 8 and expand it all out as much as possible, and then you would have it correct. Yes. So, and then one more step right over here would be 3x squared. You have 15 minus 8.
Like terms.
Yes, like terms.
This is what
Yes. So you know how to multiply two expressions. So really, let's see, you need to have 3x minus 8 right here times.
See, I started to do
3x.
that, but then I
Yeah.
got myself.
No, that is correct. That's exactly
Okay.
what you gotta do. 3x minus 8 times 3x minus 8. Expand all that out, and then at the end, have the 5. So go ahead and see if you can simplify that, because to be able to multiply those together.
So like,
You remember what's called the
FOIL,
FOIL method?
yeah.
Yes, you do need to use the FOIL. So the only thing is you combine these two like terms, negative 24x plus negative 24x, and then you All right, so this answer over here should be 3x squared plus 7, so I'll have to go back and change that, so that should be a plus right there. So yeah, the idea of f of g of x is to substitute the g in place of this x, and then the opposite occurs of g of f of x to substitute in the one x here and square it. So that's composition of functions. So even though it's not recognized at the very beginning, there are a lot of functions that appear to be more complicated, and they are, which are actually compositions of simpler functions. All right, so the concept of excluding values of the domain, and you need to interpret up here, apparently this f circle g means f of, or composition g of x. Then what you have to also recognize is that if you have various ones with specific values that are excluded from the domain at the beginning, then it must be excluded from the domain as you continue on. All right, that's all that means. All right, now a composition of a function is a characteristic that's often used, but another characteristic that really needs to be thought of is called the inverse of a function. So we'll look at the finding them and then the idea about the graphs of them as well as we think through the idea of inverses. Now, a word that often goes through people's minds, I know, in thinking about inverses that's similar but different is the word opposite. And everybody can understand what the opposite of something is. The opposite of hot is cold, the opposite of up is down, and so on. Inverses are not the same as opposites, but there is an analogous relationship to them. If you have two different functions, f and g, such that f of g of x is equal to x, and g of f of x is equal to x, they are inverses. And this symbolism right here is read f inverse of x. So what that really means in more simple language is if you have a certain function and you do certain mathematical relationships and you get a value or an answer. And then if you had another function or a value of that answer and it works back to get your original value, those are inverses of each other. So here's an example. Look at this function, f of x equals 4x minus 7. Look at this function, x plus 7 divided by 4. If you do, just as we did a few moments ago, and do f of g of x, everything simplifies out and you get x. Then, if you would go through and do all the working, it's not hard, but it is a little complicated, g of f of x also gives x. That means they are inverses. Now think about really what's going on here, because they're really just two-step problems. If you took any number you can think of, you multiplied it by 4 and then subtract 7. The inverse of that would be to add 7 and divide by 4. So, for example, you can take any number you want to, and I'll just show you how it works. Suppose we started with the number 5. What is f of 5? Well, f of 5 means 4 times 5, which is 20. 20 minus 7 is 13. What is g of 13? Well, 13 plus 7 is 20, and 20 divided by 4 is 5, and that gets you right back to where you started from. So that's really the idea of an inverse function, is you do something to some value, you get an answer, so to speak. You take that answer in your next function, work it out, and you get right back to where you started from. And it works for others as well, no matter which ones you put in. By doing it this way, you prove it works for every single value. So the question is, how do you find an inverse function? So at the very beginning, if we would have had this function f of x equals 4x minus 7, and the task before is to find out what the inverse function is, then how do you go about doing that? So here are the steps to do. So there are 4, and again, if you just look through them in these examples, doing step by step, then it's not a problem. All right, here we go. So here's the steps. So here's your original function, f of x equals 2x plus 7. You can see similar to the one we looked at a moment ago. First step, take out the functional notation and put in y. And you recall we've done that several times already. F of x is the functional notation, y is what you use when you are graphing. So that's first step. Then you interchange the x and the y values. So where the y is, you put an x. Where the x is, you put a y. Now you have a new function right here, new equation, but you solve that equation for y. So to do so, you have to take the 7 over to the other side and then divide by 2, and so then you would get y equals x minus 7 divided by 2, and that is the inverse function. So, another example, suppose we do something like this. Suppose it's a square root of x minus 9. Now, of course, you don't want to memorize these, but intuitively think what's going on by just making it in terms of y. When you reverse the x's and y's, you'll notice what we'll look at in a few minutes about the graphs. You can see how that works, and then solve for y and put it in that symbolism. So let's do that. So in changing from functional notation, put y equals the square root of x minus 9. Then solve for y, so you have to bring the 9 to the other side, and since the y is a square root, the opposite of a square root is to find the square, and so y is equal to x plus 9 quantity squared, and then to formally put it in this set of notation would be the inverse function. Let's see. Okay, that's all I need to say there. All right. Now, if you think what we said earlier about a function has to pass the vertical line test, which means you put every vertical line through the graph to determine whether it does or does not intersect at 2 or more points, that's to verify if it is a function. And since you interchange or reverse the x's and y's to find out if a function does have an inverse, it has to pass the horizontal line test. So, notice this function, this graph right here is a function because it does pass the vertical line test. Everywhere that you would draw a vertical line through here, it intersects at only one point. So it is a function. But does that function have an inverse? The answer is no, because if you can draw a horizontal line passing through 2 points, then it's not an inverse does not exist. This is a function, but it does not have an inverse. Now, on part B, the graph of this curve, if you drew every vertical line you can think of, it would intersect the function at one and only one point, so it verifies that it is a function. But now if you would draw a horizontal line through there, every place on this graph a horizontal line intersects at one and only one point. So since it passes the horizontal line function, horizontal line test, then this is a function as well. So what do those graphs look like? So just ponder that for a few seconds. The idea of an inverse function in reality is just a replacement of x and y values. And so if that happens, then you can see what the graphs of the functions look like. So for example, here is, and this was intentionally designed as a function that looks weird, as people would say, but the reason for that is to show what an inverse function looks like. So at the very beginning you say, well, this is the function, but how in the world can you get an inverse function that looks like that? Well, you can kind of see there's something going on there with the graph, but obviously in math we don't want to guess and say it kind of looks right. We need to be real precise. So there's two different ways to go about doing that. One is to think, since x's and y's are reversed, it would have something to do with what happens if you have y and x's equal to each other. So here is the line y equals x. Now, this concept, which we haven't formally studied here, and we won't, is called a reflection. So you understand, of course, the idea of reflection is very easy to think about. But what about specific coordinates? If you've got specific coordinates, you can be real precise about what the reflection is going to look like, even though this reflection across this line shows you basically what it is. So just replace points. Just replace points. So if you have this first point over here, -3, -2, reverse the x and y's. So if x is -3 and y is -2, that becomes -2, -3, which is right here. Then the -2, 2, which is right here, becomes 2, -2, which is right over here. And then the 4, 1 becomes 1, 4, which is right up here. And so just a reversal of the x's and y's of each of those points will show you what the inverse function looks like. So again, the idea of inverses is one that would, this is how you work about getting an inverse function, what it means, how you calculate one, but there's a whole lot more to actually doing them, working with them, than what we'll get into in this section, or this chapter. So, no questions about that. Then, let's move on to what will be our last new section for today. The distance and midpoint formulas and circles. All right, the distance between 2 points we'll calculate. We'll calculate the coordinates of the midpoint, and then we'll look at the special basic formulas for the equation of a circle. All right, now, as you can suspect, there's other formulas that are involved. This one is the distance formula. To compute the distance between 2 points, find the square of the difference between the x-coordinates plus the square of the difference between the y-coordinates, and the principal square root means the positive value only, because remember, a square root, such as if you were asked what's the square root of 64, technically there are two answers, positive 8 and negative 8. But when we're looking for distance, which distance is only a positive number, then you only use this right here. Now, even though we're not going to apply this to coordinate geometry, I can tell you that this formula is actually derived from the very well-known, frequently used theorem that you've seen before, and that, of course, is Pythagorean theorem. This is a different form of the Pythagorean theorem when you find the distance between 2 points. Because if you think about on a graph, if you have x's and y's as being vertical and horizontal, then the straight line distance between the two really is going to manifest itself in Pythagorean theorem. All right, so for example, here's one. If you have these 2 points, -1, -3, and 2, 3, what is the answer in both simplified radical form and then rounded to 2 decimal places? And please do note that you need to be able to do both of them, because I know in looking through the homework problems from my math lab, the authors will ask you to do one or the other, so you need to be familiar with both of them. So you find the difference of the two x-coordinates, 2 minus -1 is 3. The difference of the two y-coordinates, 3 minus -3 is 6. You square those, 9 plus 36 is 45. But notice what's called simplified radical form means you factor out a perfect square. A perfect square being the number that multiplies by itself that's a factor of 49. Well, of course, 9 is a perfect square. The square root of 9 is 3. So the simplified radical form, and that's what's being asked for right here, is 3 times the square root of 5, which as a decimal rounded to 2 places is 6.71. That really is a very important formula to know, so let's see if we can apply it using your scratch paper there handy. Can you find the distance between those 2 points? So why don't you write those 2 points down, -3, 7 and 2, 19, -3, 7 and 2, 19, and then I'll put back up here again. Here is the distance formula. So
2 comma what?
2, 19 was the second one, and the first one was -3, 7. Find the distance between those 2 points. That's fine. You're not expected to know that. If you ever would study squares a lot, then you would do them over and over and over again, and
Smokes.
they can be memorized. It's a good idea to know them up to at least 10 squared, but beyond that, that's okay. This one, the square root of 169 is 13. So in this case, even though I put these directions like what the authors say in the textbook, simplified radical form, well, technically, a simplified radical form, if it's a perfect square, is just that whole number. So that's fine. So the distance between those 2 points would be 13. And as I said, if you would graph them on graph paper, -3, 7, and then 2, 19, the actual distance of this here would be the length of the hypotenuse of the right triangle, because that's really what's going on. All right, now please keep in mind this idea when you're finding different distance, you find the difference or subtract those coordinates. And so I know people are occasionally confused about this distance formula in contrast to the next one, which is the midpoint formula. So thinking in your minds, distance is a length, of course, and a midpoint is simply a specific point. And so if you have 2 endpoints of a line segment, the midpoint is really just the average of those 2 points. It's got to be in between them. So you add the 2 x's and y's. And notice this symbolism is showing that this is a coordinate. The first one is the x coordinate, and the second one is the y coordinate. So, as an example, if you had 1, 2 and 7, -3, the midpoint of those, you would add the 2 x's, 1 plus 7 is 8, you would add the 2 y's, 2 plus -3 is -1, and then in each case you divide by 2. So x would be 4 and y is -1/2. So once again, do keep in mind the distinction. For the midpoint, you're going to be adding the x's, adding the y's, and dividing by 2. You don't subtract as you do in finding the distance formula. So, up to this point, all of the last several sections have been dealing with equations of lines. So we did the point slope form, the slope intercept form, the general form. We looked at the slope of parallel lines, the slope of perpendicular lines, how you get the equations of those. And now we focus here on one unique type of equation for something that, of course, everybody is very familiar. And it's interesting to ask people if you are not familiar before, and I do this in high school geometry classes, and saying, what is a circle? And even though everybody knows what a circle is, to formally define it is a little bit of a challenge until you see what it is. Well, a circle is a set of all points in a plane. A circle is a plane surface that are equidistant from a fixed point. And the distance from the center to the point on the circle, of course, you know, is the radius. So notice what would happen to this, everyone, if this definition has part of it removed. What happens? If you took this little phrase, in a plane, out of that definition, and you said the set of all points that are equidistant from a fixed point. If this phrase is eliminated, the set of all points equidistant from a fixed point, what type of geometric figure do you have? If it's not in a plane, it could be a three-dimensional surface, a figure, so you'd have a sphere. A sphere is the set of all points that are equidistant from a fixed point. But in a plane, then of course you have a circle. All right, there is a special formula for a circle. And once you recognize the form, it's not hard to look at, or not hard to work with also. And that is this. But notice h comma k, x and y, are the coordinates of the center, and r is the radius. And of course, if you know those two characteristics, you know everything you need to know about a circle. The center and how long it is from the center to a point on the circle, which is the radius. And of course, every radius of a circle is the same. And by the way, this plural of the word radius is called radii, R-A-D-I-I. So that's the formula for the equation of a circle. So how do we apply that? Of course, like in everything else in math, you need to apply it. So here's what it looks like. If you knew that the center of the circle is at 0, -6, and the circle has a radius of 10, then you would put 0 and -6 in place of h and k. So you'd have x minus 0 quantity squared, and you'd have y minus -6 quantity squared, which becomes y plus 6, and then of course 10 squared is 100. So looking at this equation right here, you immediately know that it's going to be a circle. So in summary, notice that if you just have an x squared and there's no other value, that tells you that the x coordinate is 0. And the y coordinate of the center is the opposite of this. So if this is plus 6, then you know that the center is actually -6. If this is -6, then you know that the center is plus 6. And whatever this value is over here, the square root of that number is the length of the radius. So that's the general form for a circle. All right? Now, you can do it in just the opposite way, of course, as well. If someone told you this is the equation of the circle at the very beginning, and you're asked to find the coordinates of the center and how long the radius is, then it's very simple. You take, this would mean -3 is the x-coordinate. This would mean that +1 is the y-coordinate. So you would immediately know that those are the coordinates of the center, and since the square root of 4 is 2, that is the length of the radius.
So why would it be -3?
Because the form is the opposite. The form always starts out with minus signs right here. And so when you get to this statement right here, x plus 3 is algebraically equivalent to saying x minus -3. And so that's why it becomes the opposite right here. Good question. Now, you not only can do it in both ways, so we took the equation we took the values of radius and center to get the equation. You have the equation to get the center and the radius, so let's do one more. How about a graph? So, there's a circle. So, what is the equation in the standard form? Well, you just need to know those two values. So looking at the graph, this point right here, -2, 2, so that would be the center of the circle, -2, 2. And you can see from here, if you count horizontally, 1, 2, 3 units to the right, then that would tell you that the length of the radius is 3. And of course, it would have been the same if you did vertical or horizontal to the left. So -2, 2 becomes the center. The value of the radius is 3 units. And so then that means we can plug it into the formula for these two values. So once again, for x would be x minus -2 quantity squared, which simplifies into x plus 2 quantity squared, and then y minus 2 quantity squared, and if the radius is 3, 3 squared is 9, and so you have the equation of a circle. Okay, anybody with a question about that? Well, I believe then that we are at the conclusion for today's lesson.